What's up, guys, and welcome back to the third part of the mathematical induction series of videos. Today we're going to do one last example. I might possibly continue them at some later point with maybe some different, more complicated examples, but for now this is going to be the last one. So this is going to focus on recursive sequences. So let's read this question. Recursively define the sequence a1, a2, a3 ... as follows. a1 is equal to 3, so the first term is equal to 3, and for each positive integer n we have an plus 1. That means the following term is equal to the term before it over n plus 2. So okay, I'll give you an example in this by way of doing this first question. Find the first 5 terms of the sequence in order. So we know a1 is 3, right? That's given. And then a2 is going to be equal to a1. As you see there, it's the previous term. So it's a1 all over 2, since that's the n, plus 2. But we know that a1 is 3, so we can just as well sub it in. And then that's 3 over 4. Cool. Then we do the same thing for a3. We put a2, which is the previous term, there, right? We have 3 over 4, 3 over 4. And then we're going to say 3 plus 2. That is equal to 3 over 4 over 5, which is equal to 3 over 4 times 5. If you don't know what I did there, I just brought the 4 into the denominator, right? Because that's just basic arithmetic. If you need an explanation on that, I guess I could quickly give you one. 3 divided by 4 is that over 5. That's just equal to 3 over 4 times 1 over 5, which is equal to, right, you just multiply the numerators, multiply the denominators. There you go, giving you guys extra arithmetic lessons for free. So then we're going to do the same thing for 4. That's going to be 4 plus 2. That's equal to 20 times 6, or 3 over 20 times 6. And 20 times 6, so you can just say 6 times 2 times 10. That will be 120. This could actually be simplified further and say 1 over 40. My previous attempt at recording this video, I didn't actually notice that. So then here you could say 1 over 40 plus 5 plus 2, that's equal to 40 times 7. That is equal to that's equal to 4 times 7 times 7 times 10. 4 times 7, that's 28, so it's 280 over 1, and 1 over 280. There we have our first 5 terms, right? We have 3, we have 3 over 4, 3 over 20, 1 over 40, and 1 over 280. On to the next part of the question. Part B, prove that an is equal to 6 over n plus 1 factorial for every positive integer n using mathematical induction. So firstly, what I want you to see is, they say every positive integer. That's very important to take note of. So that's greater than or equal to 1, which is the same as saying greater than 0 for any n, an element of z. So we obviously start with a basis step as usual. Actually, by the way, let me just explain what the question is asking. It's asking us just to prove that any term in the series can be given by this formula, as opposed to the recursive formula, which relies on the previous term. As opposed to saying this, it's saying each term can be defined as this. Okay, there. So let's start. 6, oh yeah, we're testing if it's true for n equals 1. So a1 is equal to 3, that's given. Then that's the left hand side, sorry. The right hand side is equal to 6 over 1 plus 1 factorial. That's 2 factorial, 6 over 2 factorial. But we know 2 times 1 like 2 factorial is equal to 2 times 1, that's just 2. So we can say 6 over 2, that's equal to 3. Cool, therefore the left hand side is equal to the right hand side. Therefore an is equal to, so that is true for n equals to 1. Then it's the inductive hypothesis, in which we assume that ak is equal to 6 over k plus 1 factorial for all positive integers k. Notice, just as always, we're basically rewriting this in, like, with swapping the n's with k's. So then let's do the inductive step. Test if ak plus 1 is equal to 6 over k plus 1 plus 1. Let's start with the left hand side, ak plus 1. But we know, remember what we are told, the recursive function is defined with an plus 1 is equal to that. So what we can rewrite that as, is for any positive integer k and any positive integer n, and k is also a positive integer, so we can do the same thing. We can basically do that. It meets the requirements, so we can, therefore, we can apply the same rule, as it were. ak over k plus 2 given, and given and k is a positive integer, we can also see, based off of the inductive hypothesis, that ak is equal to 6 k plus 1 factorial. So we can substitute that into this formula by the inductive hypothesis. We can say 6 k plus 1 factorial is equal to, not equal to, it's that, you can say, by the inductive hypothesis. And before I go on to the next step, I just want to explain something to you guys. So if I have k plus 2 factorial, that is equal to k plus 2 plus k plus 1 plus k, not plus, multiplied by k minus 1 all the way until 2, 1. But what you should notice is that this whole part is just k plus 1 factorial. So if we have k plus 2, this is equal to this. K plus 2 all factorial is equal to k plus 2 times k plus 1 factorial. So I'm going to quickly just move this off to the side, make it a bit smaller, move it off to the side. Then we're going to do the same trick, moving the thing into the denominator. As standard algebra in this case. Last time it was, it's, I don't know why, but I just feel like the k plus 2 should be on the left. That's not anything mathematical, that's just OCD, not real OCD, but you know what I mean. Because of this, we can see, because of this thing here, this explanation here, that this is equal to this, we can say that this is equal to this. That's equal to k plus 1 plus 1, because we want to get it in the original form, in the original form that we're trying to prove, and that's equal to the right hand side. Therefore, true for, let me not say true, let me say therefore ak plus 1 is equal to ak, no, not ak, 6 k plus 1 plus 1 factorial. And then let me just write the conclusion and I'll be back. Therefore, by the principle of mathematical induction, we have shown that an is equal to 6 over n plus 1 factorial for all positive integers n. That's all for this video, guys. Please consider subscribing, liking, and sharing with others. I'll see you in the next one.